get started?
Yep. See that.
Okay, okay, yeah, I can provide a quick intro, I guess, if that helps, but to everyone who's here. But yeah, really excited to have Tim Darcet here to present his work on CAPI. So, for context, Tim is a researcher at FAIR in Mena Paris, and he's been working a lot on self-supervised learning algorithms. So he was, working on DINO v2, DINO v3, working on VIT registers, all kinds of really cool and influential work in the space. And of course, we've been thinking a lot about self-supervised learning for medical imaging and, for both the pathology project that we have going on with the nanopath competition that we have, but also the neuroimaging stuff as well. So, we thought that it would be great to have Tim present his latest work on his new self-supervised learning algorithm, and maybe is useful inspiration for us as we are coming up with new ways of doing SSL for medical imaging applications. So with that, I will let Tim start the presentation.
Great. Thanks so much, Tanishk. Can everyone see my screen? Great. So hi everyone. I'm Tim, as Tanishk said. Yeah. So today we're going to talk about CAPI. Maybe the only precision I might add is my latest work is not that latest. This came out like a year and a half ago. So there's some like things that are not really up to date in the sense of what comparisons we make, etc. It's not the latest soda, but well, I think it's still a relevant work, in particular in the thought process. So let's start talking about CAPI. And for that, the first thing I want to stress is SSL for visual representations works. Maybe it goes without saying here if you're saying that you use SSL, but it's not obvious to everyone. The fact is that, especially in the space right now, vision for people is generally talking about VLMs. So generally talking about benchmarks that are very OCR focused. So clip models are very important. And not everyone knows what SSL is really useful for. And the fact is that I think there are like some domains in which you cannot just do without SSL. Just SSL is just strictly better than anything else we've got. And we started seeing that with DINO v2. And so one thing is, for some domains, we just don't have much annotation: medical, satellite, reference, biology. Of course, about medical. These are examples of applications of DINO v2 that were like put in place. This was RayDINO, this was Canopy height map estimation, this PlantNet, and this is, I don't remember which one, but one of the histopathology models that are based on the DINO v2 recipe. And these models, they work very well thanks to self-supervised learning. Another thing that can be emphasized is that there are some sorts of an image understanding that are just not well captured by clip models, such as depth estimation, like anything that's geometric, point tracking. This is, for example, depth estimation. I don't remember which one it is, maybe Depth Pro or something, but a lot of depth estimation models that came out after DINO v2 used DINO v2. Also for point tracking, it works very well. Also, if you want to do things like neural feature fields, where you have features for different objects in a 3D scene. Now, all of these things justify the idea that we want to have good SSL. Now, that's great. And with DINO v2, so again, slightly outdated. Now we could say the same thing with DINO v3, but it's just this was made at a time of DINO v2 being very prevalent in the field. With these DINO models, we've got something, but it's complicated. If you have ever tried training a DINO v2 like model, if you have ever looked at the recipe, it's a mess. I'm allowed to say it because I made it, but it's really complex and messy. Nobody likes the recipe, especially not us. This, for example, is a diagram of the that comes from the iBot paper on which DINO v2 is based. It shows how the iBot and DINO v2, which took the same things, mixes like global loss, local loss. It's a bit complicated. Also, I would like to say, I think it does not scale super well. Now, this is, of course, a bit maybe controversial to say because, well, DynoV2 is scaled, and now we've got DynoV3, so it's even worse. We've got pretty big models, but it's hard to scale them. Like even just getting to 1B scale, which is not very big by today's standard in NLP, and even in vision, like in 2018, there were like 700 million parameter models in like ConvNets that existed. So 1B by now is absolutely not crazy impressive for vision, and it is not really going in the general philosophy of the field of um, we made simple methods that work well and that benefit well from scale. To scale DynoV2, we had to fix a ton of things. Just every time you scale, you get some subtle ways things break, and if you train for too long, the model just gets worse instead of getting better. You have weird things. I don't like it. Finally, DynoV2 has noisy feature maps, so this is in particular something that is important to state, especially after the fact that we work on registers to introduce to fix the artifacts that we found in DynoV2. But the fact is that even with registers, this is a bit noisy. You see, those are feature maps with registers. They are not very clean, very crisp. And not sure why, I gotta be honest, but it makes me think something's wrong with the method, and I would like to just strip it down to just make it bare and to understand each component instead of just adding and generating things on top of each other. And makes me want to say, can we do simpler? Of course. And so the process is very simple. Say, okay, let's simplify DynoV2, or let's look at the DynoV2 loss. What is it? It's the sum of three losses: the loss of Dyno, the loss of ibot, and the Collier loss. Now, what are those? Dyno, if you are familiar with DynoV2, you might be familiar with Dyno. So I'm assuming maybe a lot. Maybe some of you are not familiar at all with any of those. Well, deal with it. I mean, but yeah, basically it's just the loss that DynoV2 is based on. It's been there for a while. It's well studied in a sense. Like a lot of people have used it, and we kind of understand what it's supposed to do. In a sort of contrastive learning sort of way, we have an idea of how to interpret it. The Collier loss is something we introduced in DynoV2 compared to DINO and ibot. It's a very small loss, the regularization term. And honestly, like we also have an idea what it does. It just spreads around the vectors in embedding space. And it does not play a huge part. Like you can remove it or add it to have a plus or minus 1 point on benchmarks. It's not a make or break thing. But the ibot loss, I think, is interesting. It is actually something, maybe not mysterious, that's a bit dramatic, but it's actually something worth checking, I think. Why so? What is ibot? Ibot was introduced 6 months after DINO, so actually a while ago now. It was the SOTA in SSL until DynoV2 for a long time, even though like not many people noticed it, but it was like at the top of benchmarks, just people didn't look at benchmarks. And so it worked well, and that's why we ended up taking it for DynoV2. We're just like, okay, how can we make something better than DINO? Well, we check the benchmarks. The top thing, like the only thing that adds on top of DINO is the ones that add this loss on top of DINO. So we take it. But even in the original paper, ibot loss was combined with the DINO loss. The ibot loss does not go alone. But it is very important for DynoV2. It's not a trivial thing. It is like an important improvement to the model to add the ibot loss. This is a table from DynoV2. Obviously, like when you add the ibot loss, we have small improvements here and there, and we have a big improvement in segmentation. ID20K is segmentation benchmark. Plus 3 points is a very non-negligible improvement. So it is a big win. Clearly, what's weird is clearly the ibot loss brings a signal that is not present in the DINO loss. It adds something on top of that. We tried, but we could not get the same performance without ibot. But even though it is a better loss in the sense that it adds more signal, it seems to have more information, it is not working alone. It needs DINO. It just does not work alone. And finally, it's a bit, again, as I said, it flew a bit under the radar. It's very much less cited than the most cited models in SSL. So I think it's not very well studied. And so this really points me towards thinking, it seems like iBot is the right idea, just not done right. The loss is weirdly formulated. It is super unstable. It does not work alone, and so they add the DINO loss as a duct tape to make it stable, but it's not really perfect. But it is a great idea because it seems to capture a signal that is not there in other losses. So let's study it, of course. And if we want to study iBot, we are actually studying masked image modeling. That's how they call it in iBot. Basically, masked image modeling is super simple. You say, you take an image, you remove a part of it, and you try to predict what was removed, what is missing from the image, and you create a model that tries to predict that, and it's a good pre-training task. There is, of course, the concept of MAE, if you've ever heard of that. Masked autoencoders work this way, but many different methods before and after MAE are based on this concept. And what we're going to do is to try and formulate a framework, a kind of idea of, okay, what is masked image modeling? What are different components? And can we unify things? Can we see all these masked image modeling methods as different aspects of the same concept? And so the way we formulate it is like this. On one side, you've got a full image. On the other side, you got a partial image. You masked out something. Now, this full image, we're going to represent it somehow. You split it into patches, and the representation might be just the raw pixel values, or it might be some kind of encoding of those pixel values. Maybe you're going to use a model or whatever. That's going to give you a target that you try to predict. The encoding of this patch, the representation rather of this patch, whether it is the raw pixel representation or something more complex, the representation of this patch is a target. And on the other side, you have a model you train. It takes the visible patches. It takes some kind of query of, let's try to predict what is here, what is missing. And you make a model, whatever architecture you want, and outputs a prediction, and then you compare the two through whatever loss you want. Now, those are missing boxes, and we're going to fill them up one by one by choosing which components to use. The first we're going to explore is the target representation. And as I mentioned, if you've ever heard of MAE, this is the simplest case. You just take the pixels, and that's your target. In a sense of vectors, you might want to say, okay, pixels is a patch of 16 by 16 pixels that have 3 channels each. You flatten that, 16 by 16 by 3 gives you 768 channels, and you have a big vector of 768 values that you try to predict. Simple enough targets, it works. And that's something worth noting, is simple, stupid, it works, and that's perfect. It is an idea that existed before and after MAE, and that is just, it's just in painting, like if you go back in computer vision literature, you're gonna find in painting work that's just same thing as that in different words. The issue with that is, I'm gonna say it's a bit opinionated, to be honest. Like it is my personal take on this. Maybe I'm wrong, but you are targeting directly the pixel values, so you focus a lot on color and texture instead of the semantics, I think. Like if the student sees these parts and tries to predict here and predicts, I don't know, a full black image, well, it's going to have a not too bad loss because most of this patch is black. But it's going to have a much better loss than if it predicted something like a fully brown dog. A fully brown dog would have a very high loss because the pixel values are very different. But it's not really correct. I would not like that for my pre-training objective. Like a fully brown dog is a pretty good guess for what is missing here. It is actually a very reasonable guess. It is likely to be that. You can't guess the entire color of the dog just from the head. And so I would like a loss that gives a better scoring, that gives more importance to semantics rather than color and or texture. In practice also, to have some empirical data, the representation of the MAE model and the models that are derived are not too great. Representation meaning like the frozen embeddings, if you try to like use them to do retrieval, KNN search, to like probe some information in it with a linear probe, it does not work super well. Now, if you want to have a more semantic target, a more focused on the concept instead of the colors, you might say, okay, let's try to use an encoder. A pre-trained model, you take an encoder, you freeze it, and this is now what converts your patches into representations. It's an idea that exists in the literature, and that was actually like the first modern use case of massive image modeling recently called BATE. Like the first massive measurement method that used vision transformers, basically. Recently, after vision transformers, people tried using a VAE to convert these patches into discrete tokens, encoded, and then predict them. It works, but the representations are not great. Why? Not clear, to be honest. This is my own interpretation, but I think if you take a discrete VAE, you look at the representation of it, they are still very focused on pixels and textures. They're not highly semantic. And the representation of this patch is going to be a vector that describes a little bit maybe the class of it, but mostly what is the color, what are the exact textures, etc. And that's just because of the way it's trained. It's trained for reconstruction. You can also use, for example, what EVA uses. EVA is a series of pre-trained vision encoders that are, it's a complicated, a bit messy line of work, but they do mass image modeling in the latent space of a clip. The issue is that clip has pretty bad feature maps, to be honest. Like, if you look at the local embeddings of a clip, they are quite decorrelated from the actual information just underneath. They're very noisy. It's a bit weird, and so I think it's probably not the right target. But my main issue with this approach, and again, this is very opinionated. So far, like the first section, about choosing the target representation is just fully opinionated. I'm just giving what I think is the right way to go forward, but many other people might disagree with it. So my main issue with that is, right, suppose you actually use a frozen encoder, you train a good encoder this way, you have like your targets, you have whatever loss, and you have whatever architecture, and you have your new model that you train with that. And it works in the sense that your new encoder is better than the frozen encoder that was used to produce the target representations. Then, well, why not use this new model you just trained as a target encoder for new training? That's something that is very natural to do. Like, if you train a better encoder, let's use it. That is actually the idea of a model called DBot. As an aside, so DBot is a successor to iBot, and is basically what they did. They start with a random of pre-trained teacher, and they train a student with mass image modeling, and then use that student as a teacher, and do it again and again and again. And the very natural conclusion of this is, why do you do things step by step when you could do them online? Especially when we have a very useful online teacher-student technique in the SL literature, that is to use an EMA of the student as the target encoder. I use a bit interchangeably here the word teacher and target encoder, and the word student and online encoder. Those are just, they are used a bit interchangeably because of the background literature in SSL. Why not use the EMA as a target encoder? There is a very natural way of doing this whole loop of training a new target encoder and training a new one from that, etc., but in a more online manner, which is going to be more streamlined and just going to be naturally going up and up and up. And as you train a better model, it creates better representation that trains a better model, etc. It's a self-reinforcing loop. So online model, that is what I propose to use. I mean, it's not my idea, it exists. It's just my idea that I'm trying to convey is this is the right way to do things, because anything else would be just intermediate steps towards that. We do something similar to DBot, but we do it continuous. Also, adding EMA adds weight averaging, and for some reason it's good. Don't ask me why. It's a mystery of just not SSL at all, just ML in general. But why does averaging the weights of different models give a better model? Nobody knows really, but it's weird and it works. And as in many cases in this field, if it feels and it works, just don't ask and use it. But it's hard. When you do something online like that, it gets messy because the target moves around, and so anything can collapse at any time, and your task is not a cleanly defined task, because since the target moves around, then the loss might go up instead of going down, and that might be a normal training loss, and you can't really debug that easily. But it's hard. But we choose to do these things because they are hard, not because they are easy or something. And therefore, if it's the right thing to do, let's try to make it work. As I was saying, people did it before. That was the case in iBot. In iBot, they did that, but it was so unstable that they added another loss on top of it to make it work. And that was the case also in Data2Vec and IJPA, which are the most similar works to ours. Yeah, it's the same idea. Now, this is for the first, if you remember the diagram at the beginning, I should have put it back here. If you remember the diagram, this is the first box. Target representation. How do we convert our target image, the specific patch that is missing from the student? How do we convert it to a target representation? Well, we're not going to use it raw. We're not going to use a frozen encoder. We're going to use an EMA encoder. And that is our philosophy. Now, for the rest of the design choices, the two other boxes, we're just going to detail anything that exists, propose something or not, and just test everything and take the best. That's just how it works in this world. So, second box, loss formulation. You might say, why do you even talk about this? Just take a distance between prediction and target and do whatever you want, L1, L2, and this is a loss and it works. Yeah, it does work. This is directly what MAE or IJPA does. MAE uses probably a root mean square or L2, I don't remember. IJPA uses an L1 loss, smooth L1, sorry, Uber, basically. Yeah, it is a very reasonable thing to do. The reason we talk about it is because iBot does something so weird that we have to discuss the difference between iBot and the rest. In iBot, the prediction and target are projected through an MLP, and the target MLP is an EMA of the prediction MLP. This is something that is just copy-pasted from DINO. Basically, it's just iBot was like, okay, let's use the DINO loss in another setting. And I kind of take issue with that because I think it's not a very satisfying idea. It feels weird to me because in DINO we have some sort of interpretation of what it was doing. It was kind of doing an implicit clustering, and here I just cannot interpret what this is supposed to do. I have no idea. Like the MLP is going to be trained to match the prediction to the target, and then the target is going to be having the same MLP but with no gradient here, and I just don't know what the optimization dynamics are going to do here. The reason why I say it is different from DINO is that in DINO you were applying this MLP on the CLS token on the student side, and the EMA of the MLP on the CLS token of the teacher side, which is a CLS token of the EMA of the student. So you just have something very symmetrical, that you have a CLS token on one side, a CLS token on the other side. They are processed through the same thing, and in a sense, you are just projecting two equivalent things to a different subspace, and you take the loss here, whatever. Here you have something that's fundamentally different. Prediction and target come from possibly different models, different networks, and they don't have the same meaning semantically. And so I'm like, I just don't know how to interpret it. Now you might say, hold up, why do you say DINO head is doing a clustering? I might not spend that much time on this. We can come back to it in the questions if you want to discuss it more, but short story is, this is the DINO head, X L2 norm, blah, 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 last layer, softmax Z. The last layer, if you consider the big last layer matrix, you can say that the rows of this layer is like prototypes. And when you apply this last layer on X, it is like taking a dot product of the prototypes with X. since you have normalization that is applied to X and possibly also to the last layer's row, this loss product is a cosine similarity. And so your logits are cosine similarities of rows with X. And so when you take a softmax of that, there's just a soft assignment of X to the WK. And so you have a soft assignment of a vector to prototypes, and you kind of optimize something that looks like that looks like a soft kind of k-means. Like since both student and teacher side are very symmetrical, you have x prime, z prime, just EMA. The only difference is that the weights are EMA of each other. You could imagine, okay, this is the loss, the cross entropy loss. If you really had perfect symmetry, like if the EMA was momentum 0, and so z equals z prime, then this loss is not a cross entropy, it's just the entropy. And if you try to minimize the entropy of something, is you're pushing it towards a very peaky distribution, towards hard assignment. And so since you're optimizing that with respect to the weights of this last layer, so in our interpretation, the prototypes, you are basically pushing the prototypes towards in the direction that makes the assignment more peaky, that makes the assignment just more clustered. And so you're just moving the row vectors towards basically the average of the zk that are assigned to it. So it's really some kind of inline k-means. We can come back to it because I feel like this is maybe a bit involved for a very short explanation. But that should explain my point of DINO. I can understand why we are doing this loss with the head, etc. In iBot, I don't understand because this just doesn't apply. You don't have the same thing on both sides. It's not x and x prime. It's just different vectors. It doesn't work. So what I propose to do is, all right, forget about all this. If it was a clustering at the beginning, let's use a clustering explicitly. Like let's design some kind of projection head on top of our target that is explicitly designed to do a clustering. And then our prediction, well, if it's not the right dimension, we just put it through a linear and then you do a cross entropy loss. What is very nice in that, apart from the fact that I'm just trying to reproduce the original idea of the MLP head, is that it's what I call debuggable in the sense that I know what the components are supposed to do. This is supposed to produce a clustering. I can visualize this clustering. I just dump images with the clustering overlaid on top of the image and see the clustering look semantic. I can see if the clustering is sharp enough or if it's moving around too much, etc. So it is interpretable. And yeah, basically you only apply the clustering on the targets and the prediction, you try to predict this. It's a bit nice in a sense, because like in the original example that we had of our dog where we try to predict what is in the middle that is not visible from the student side, well, if we are correct in our interpretation that this clustering is going to produce some kind of pseudo-semantic segmentation without labels of all the visual concepts, then what we're going to predict here is not the pixels of the dog. It's going to be the kind of label that is probably going to be something like the body of a dog. And so we predict really the semantic aspect instead of the just low-level information. And we can double check that this is happening by visualizing the clustering and seeing whether what appears like what clusters together is really like dogs clustered together in the semantic space. So it's really nice. So that's what we propose. And the question is, does it work? And yes.
Sorry, Tim, could I just ask a quick clarification question? Do you do the loss on just the mask patches or on all the patches?
Yeah, mask patches only.
Did you ever try to do it on all the patches, or?
So we're gonna discuss it after that, but due to the architecture I chose is that there's a predictor that's only really makes sense for mask patches. You can't really apply the predictor on the visible patches in the architecture I did. But in architectures that are more similar to iBot or to IJPA, you could do it. I don't know how well it works, to be honest. Yeah, maybe.
Okay, maybe we'll discuss more later.
Yeah. No, yeah, I don't have data on this. I think I feel like we've tried it at some point a long time ago in a very different setting, and it did not give anything, but I'm not sure. That's very vague answer. All right, let's discuss it afterwards, maybe.
I have a question too.
Yeah, sure.
When you cluster, wouldn't that mean the prototypes are limited to what's in the training data? Like, how will the model translate outside of images and features not in the training data?
So, yes, to some extent. So know that the prototypes here, the clustering here, maybe it's not clear enough, but the clustering is soft. We don't assign like a hard target. We assign a soft target that is therefore very informative. It's still like a soft vector that has basically as much information as the embedding before, just in a different shape, in the shape of a distribution where everything is between 0 and 1 and sums to 1. So you still have all the information. Now, if you applied this clustering to something that is absolutely not seen in the training data, yeah, it's possible that it would do like just not work. Like the clustering would go crazy or just assign to very weird clusters. Maybe. I'm not sure. Maybe also it would assign to like the reasonable closest things that exist in the training data. But what's sure is that this is purely a training device. The model does not include this. The model in the sense of what we're going to use downstream for downstream tasks. It does not include the clustering. What we're going to use downstream for the downstream task is just the encoder that is below that. And these are just things that are used for training these encoders. But yeah, the encoder might encode this more acceptably if something is not in the training data, the encoder is going to encode what it sees, maybe in terms of components, if the components are recognizable. But yes, and also like in a sense, if a concept is not in training data, you can't really expect much from a model. Like if it's not there, the model cannot learn anything about it. Does it answer the question?
Yeah, thank you.
All right, let's move on. Don't have that much left anyway, so we can discuss more later if you have more questions. So the question, does it work? Well, empirically, yes. So we try to compare. So in the 3 different losses I described, this is I give an example of a direct loss. So no head, just compare directly with some kind of smooth L1, the prediction and the target, and it trains. It trains just not as good. If you do the iBot style loss MLP with iBot, well, if you do it alone, it just does not train. iBot does not work alone. As I was saying, it does not really make sense, this loss, in my opinion. If you do MLP with CAPI, whatever, it's not as good, and just CAPI loss works quite well. Of course, usual caveat apply, which is that, of course, this ablation starts from a setup that is a bit optimized for CAPI. Like, I don't know, the hyperparameters might not be the exact right ones for the other ones, but still it seems like the CAPI loss works. Now, the last point in this whole build your own massive image modeling method that we've been doing, last point is predictor architecture. So as I was saying, there are actually some subtleties in the architecture of the predictor. Multiple methods use different things. It might seem like trivial, almost a hyperparameter, but it actually makes a lot of difference on how well the method works. What do I mean by architecture? Well, once you have these patches, like your visible patches and your masked token that is not visible, how do you obtain your prediction? Well, the first methods, be it an iBot and also other similar methods, used a transformer, single transformer that is just both encoder and predictor. And this transformer takes all of the tokens and gives out a prediction. And often in the teacher-student setup with like the MA, this full transformer is EMA'd into another transformer that takes only that takes all the visible patches to produce a target. Whereas what some people did some people being MAE and IJPA basically, is to split the encoder and the predictor. In MAE, it was a good argument for efficiency. In this diagram, it seems like there are not that many mass tokens, but here is just 1 out of 4 tokens. But in MAE, it's actually 75% of tokens that are masked. And therefore, since the encoder is generally bigger than the predictor, you have a lot of efficiency gain by not having all the tokens go through the encoder. This is very efficient. IJPA did the same thing. They got inspiration from MAE. In this setup, this is the encoder that gets EMA'd to view all the tokens. So it's not really the same as here. Here you split it and the predictor is only on the student side. Now, this makes sense also because, well, you encode visible things, you don't encode a mass token. It does not make that much sense in terms of the name of things. But now, if we go one step further, you don't predict mass visible tokens. You should only predict mass tokens. And therefore, you do this split cross-attention predictor, where the encoder only sees visible tokens, gives out embeddings. The predictor only sees mass tokens and cross-attends to these embeddings to produce the prediction. This is something that was actually already in the literature in cross-MAE. I didn't know about it. But yeah, it's slightly even more efficient and even more like, it's just separation of concern, encoder encodes, predictor predicts, and that's all. Yeah, sorry.
Did you come up with cross MAE and then somebody, like a reviewer, said like, oh no, that's a paper already?
No. I mean, I proposed using that, and I don't know if it was a review. Maybe a reviewer told us like cross MAE exists, and we're like, oh, okay, sorry, and we added it.
Fair enough.
But yeah, I just didn't know about the paper before. Yeah, well, what is the right choice among these three? Well, the one that says ours, of course, because else we wouldn't have chosen it. The fused setup is very common and is very unstable in my experience. It does not work super well. Speed and self-attention is more stable, but the cross-attention is what I had most success with. It's very unique. I like it. But then again, it's really just architectural choice. You just ablate and you choose whatever works best. Finally, a few other sensitive hyperparameters that we might discuss. Again, you might say it's not really part of the method because it's such a small thing, but it actually makes a lot of difference. How do you mask? So masking randomly, masking by block, masking by inverse blocks, meaning like you just keep a block and you mask everything else, and possibly adding plus roll. What do we mean by roll is when you compute the mask, after computing the mask, you do a random circular permutation. So like you have your mask, how do I describe this? You shift it like towards the right, a random number of steps. You shift it down a random number of steps. And whatever goes out of the image, you wrap it around to the left and upper side of the image. So you just shift your mask randomly. Why is this useful? Because if you like block masking, you end up masking much more the middle of the image than the sides of the image. If you do inverse block, that's the opposite. You end up masking much more the sides of the image than the middle of the image. And depending on your data distribution, those might not hold the same information. And also, if you have positional encodings that are per position, that might get trained weirdly if they don't get as much masking, etc. It just evens out the whole thing. Every position is masked as often. You just spread around the masking and you are happy. It works. It actually works very well, more than I thought. But yeah, these are the results of the ablation. You do inverse masking and roll, and you get good results, and that's nice. Number of registers. Why is this important? Debatable, but you really need registers to do this. When I added one register, it made a huge difference. When I added more than one, like 1 to 16, it made another big difference. I think the point is that registers reduce the amount of artifacts that you can see in the feature maps. And in a CAPI-like training, in a latent mask measuring training, well, the artifacts in the feature maps are not just like annoying downstream. There are also just noise in the training process, because again, these feature maps are what you use as a target in your training process. And so if you have artifacts in the feature maps, you just fuck up your whole target, you just fuck up your whole loss, it makes no sense, and the whole training starts scrambling, and that's actually a big problem that appears again and again in CAPI and in most latent massive image modeling settings I've seen. Having registers helps alleviate that quite a bit. It's nice. Now, final results of this whole thing that we've described the method. We compare to various other models. We compare on ImageNet 1K training and bigger dataset training, and none of the architectures are comparable because no one releases the same architecture, so we do what we can. But all in all, basically, the graded out models are the ones that are not just purely mass image modeling, that add something else. So iBot adds a global loss. DBot, I think, starts from something else, maybe some clip, and adds a global loss. DINO v2 has a global loss, of course. The black ones, IJPA, MAE, Data2Vec2, BEIT, IJPA, AIM, they are all basically kind of pure mass image modeling in a sense. They don't use any other loss or any other model. And compared to other pure mass image modeling methods, we work quite a bit better. So this is on classification. Across the board, it works well. On bigger dataset trainings, I trained 3, or one on ImageNet 22K, one on, oh shit, I forgot to change the name, but this is LVD, basically the same as DINO v2. And this is places, it's not that big data set, but 4 million images, but very non-object centric, which is quite nice. We can see in the next table that, well, first, it's good for places classification, unsurprisingly here. And yeah, all in all, it works well, much better than the others, especially on large data sets. We get a huge boost, whereas other methods did not really get much boost. Like IJPA on ImageNet 22K was not better than IJPA on ImageNet 1K with a smaller model. So it's nice. What I wanted to show is that, in particular, when you look at dense preference segmentation, so doing segmentation with either a KNN probe or linear probe, it works super well. It works super well compared to previous mass image modeling methods. The gaps are a bit stupid. Sometimes like 35 against 18 is absurd. Training on places is super effective to be able to segment images, to have non-object centric images. Your training data works super well. 35 here is super good with KNN segmentation. And it's actually better than DINO v2 plus reg giant on the same data set. Now, it's not like an absolute win, because if you compare on the other data sets, well, these places 205 trained CAPI is not better on the other data sets. On Pascal VOC, it does not outperform DINO v2 plus reg. On Cityscapes either. So DINO v2 plus reg is just not the best here, but it is the best balanced all-around good model. And also, if you just train on the same dataset, which is more comparable, this last line, CAPI, is not as good as DINO v2 plus reg. Not the same size again, so not perfectly comparable. But all in all, much better than what existed before in massive image modeling. Not SOTA SSL yet, but who knows? Yeah, I like looking at visualizations like PCF feature maps. This is what I was showing at the beginning. DINO v2 plus reg has noisy feature maps. Do we have better with CAPI? It's quite a bit better. It's pretty smooth, pretty semantic. Now, something I want to point out is the fact that sometimes people tell me, well, MAE has very smooth feature maps too. That is true. That is true. But why does it have smooth feature maps? Because it encodes the color, basically. Why do I say that? Well, if you look at all these pairs of legs, you have 2 pairs of legs that have pens on, one that does not. In CAPI, all of them have similar embeddings. It seems they're all pinkish. In MAE, the ones that have pens are pink, the one that does not are green. green being the same color as the mountains in the background that are white, pink being the same color as this mountain, which is more black. So what you notice is that actually pink versus green is actually just representative of whether it's light or dark colors, and not representative of what class it is. Here, the legs are one class, the sky is another, the mountains are another. You seem to have a much more semantic representation going on, and while at the same time keeping a pretty smooth and less noisy aspect. So it's nice. Yeah, that's basically all. Thank you very much for watching, for listening. Code and models available fully, like the 4 main CAPI models, bit large on 1K, 22K places, and LVD are available. Small summary of the method. You get some patch representation with the MA teacher, you cluster them, and you predict the category of missing patches. That's just what it is. It's quite simple. These are scaling plots compared to other models. You can see that it just works better at every scale. The gray one being 9OV2, which we don't beat. And you might say, why don't you just keep going forward? And this is kind of a plot, graph crime. But if you go forward, I did not manage to get it going forward. Basically, I tried training a bigger model, and it was getting some weird instabilities. As I was scaling up, the instabilities were getting worse and worse. And so it does not beat DynaV2 for now. Thanks very much. And if you have any question, of course, that's now.
Yeah, thank you for the presentation. This was really, really useful, really interesting, and it's a good overview of like all the other SSL methods as well. So this was actually really, really nice walkthrough. Yeah, I guess if anyone has any questions, feel free to unmute yourself and ask.
Hey,
Hey.
Thanks for the presentation. Can you talk about the instabilities you were referring to when scaling up this model?
Yeah. Let me see if I have a slide for this. This is a normal loss. And then I see if I have a instability loss. Normal loss is very smooth and it's very satisfying, especially if you train an iBot model. The iBot loss does not look like that. It is a mess. But sometimes, I don't remember. Oh no, I'm sorry, I don't have a slide for it. Sometimes the loss is not smooth. Just sometimes, all of a sudden, the loss starts wobbling weirdly. Potentially it starts going upwards, wobbling. Sometimes it drops down, wobbling. It's not even very consistent. I tried a lot to fix it, and I did not manage. But only know sometimes the loss starts going crazy, and at the same time you have this, then all of the evaluation curves start dropping down very sharply, and things go wrong. I say all of them drop down very sharply. That's actually a bit wrong. Classification metrics do not drop down as fast. Sometimes they keep going up for a while, even though the training is already going awry. But some metrics are more sensitive to these collapse than others. They are like more warning earlier than others. And the KNN segmentation metric is the one that I found to be a very good early warning sign. It's very sensitive. Just if the embedding starts being noisy, KNN segmentation starts just not working anymore, and you can detect the collapse this way. As I was saying, registers helped a lot for that. Having a bigger predictor helped quite a bit. Having larger, higher masking ratios, I think, helped quite a bit. And I think that's the main things I found that helped, but I could not find like a reliable fix. Those are kind of duct tape that fixes it for a while and then it comes back. Hope that helps.
So do you know where exactly, like why exactly it was failing?
No. If I did, there would be a much better model. No, I was just observing weird behaviors, bad performance, and was not able to find a satisfying explanation.
Thank you so much.
No worries. Hassan, you were raising your hand?
Yeah, how do you optimize the K and the clustering, and I asked this because we fine-tune these ImageNet or natural image pre-trained models onto totally different domains. And I'm curious about how that affects moving to a different domain that will have a totally different set of features.
So how do I optimize? You said the KNN clustering?
Yeah, the K-in clustering.
The KN. Wait.
Yeah, so you have this clustering step.
Yeah.
How do you know how many clusters to break into, for example? Or do you use something like
yeah, okay, I see. Honestly, that's vibes, those ablations. I think I started with the DINO number, which was 65K. That's a lot. That was very heavy and quite annoying to wield, especially since in DINO, like the projection matrix is only 256 by 65K because there is a down projection before the this last prototype layer in the DINO head. In CAPI, there's no down projection, and so I had a full 1024 feature vector being projected into 65K, and so there's just 65 million parameters in your head. That's a bit heavy, and if you want to train small models. So I just reduced it, and I went for 16K, and I saw like basically no reduce in performance. But I think you could go even smaller than that. I think in a sense, like it's useful to see it as a clustering, but it's also useful to sometimes not see it as a clustering and see it just as a projection to another subspace, to another embedding space, which we will apply softmax to, but that's just losing 1 degree of freedom, so it's just same thing. And in this sense, 16K is actually even like overkill because you only have 1000 degrees of freedom before. So likely that there would be a recipe that just projects to 1K and still has the same information and the same performance. But my recipe was with 16K, it was working, so I just did not touch it too much.
Do you have thoughts or experience in fine-tuning this model to a different domain?
No, sorry.
Because
no, certainly not.
Right.
Go ahead.
I'm thinking about like, if you start fine-tuning, everything may collapse into a few regions in the space.
So I think if you start fine-tuning like with the CAPI loss, the idea is you're gonna want to warm up the clustering so that it's suitable for the new domain. This should have happened pretty naturally with the fact that the learning rate is warmed up for both the main model and the clustering across, I think, 10% of the training. So like if you do a big training of 500K steps, you have 50K steps to warm up, where the clustering is going to start moving very slowly at the beginning and the predictor too. And so before we actually do substantial loss, you will have had time to adapt the clustering. Maybe if you want to go even further in this direction, you could like warm up the student slower than the clustering and like have the clustering have almost no warm up to be able to learn very fast at the beginning the new distribution, cluster it well, and finally when it's well clustered, you start training the student on that.
Thanks.
Thanks. Bharat, you have a question?
Hi. Yes.
Hi.
So one of the issue in the DINO V2 training was that the DINO V2 loss doesn't necessarily correspond to better performance on downstream tasks. Like the loss going down didn't guarantee that the downstream task performance also improves. That was also on the critic. So in the CAPI losses, so did you find any such correlation that the CAPI loss going down correlates with the better downstream task performance?
So yeah, clearly in DINO V2 you don't have any correlation. In CAPI, kind of. I did some correlation plot at some point, but I don't think I have it in the final paper. The general thing is, if you do correlation plot on a single run, first you have this bootstrapping phase where it's just not going to be correlated, just doesn't work. So that's a first confounding thing. You cannot trust the loss during the bootstrapping phase. But if we exclude this bootstrapping phase and we consider only the loss in the like 90% of the last 90% of the training. Well, if you do correlation across only one training, clearly you have loss going down and performance going up. So you're going to find correlation, unsurprisingly. The question is more, do you find correlation across runs? Like, does a loss of 5.2 mean something that is consistent across runs? And I had what I was saying, some kind of slightly unclean experiments showing that it seemed to be the case, but did not have these cleanly, properly done enough to include in the last paper, so I cannot say that with certainty. But clearly, it is already much better than DINO V2, because DINO V2 or DINO, you can have the loss going up and the performance going up too, and they're just anti-correlated for sometimes. So yeah, it's unclear.
Yeah, thank you. Yeah. So I just had one more light question on the clustering idea. So is the clustering idea, so we have the softmax classes, like it could be like 65K classes or so. So is the clustering same as saying it has so many classes, or is the idea itself completely different? Because you're still considering it as the output of the softmax.
So are you talking about the clustering interpretation of DINO I mentioned?
Yeah, yes.
So yes, in this interpretation, the clustering is in 65K clusters, each cluster being represented by one prototype. There is one row in the last layer's weight. This clustering happens in dimension 256, the dimension before the last layer. And this last layer weight is of shape 256 by 65K and has 65K prototypes of dimension 256. Did I miss part of the question? I don't remember.
No, yeah, I was just coming to this detail itself. So I was just trying to understand the softmax classes at the end of the network to the interpreting that as clusters.
Yeah.
So are both the same, or you derived one from the other? The idea of clusters from the classes.
Sorry, what do you mean clusters from the classes? Sure.
No, so at the end of the softmax, you can see that as like a classes. Yep. Each of the input as a classes. So the clustering is also coming from the same block, the idea of clustering.
Yeah.
So each of those classes is seen as a cluster, like a cluster center or a point class.
Yeah.
Okay. Yeah.
Yeah. I think maybe there's a question of how you call things, but yeah, definitely classifying and clustering are kind of different sides of the same coin. It's just clustering is kind of classifying without labels, just have to find the labels yourself. But here the loss is clearly, yes, a cross entropy loss with softmax. There's something very similar to classification too. It's just the labels are found by itself.
Yep, thank you.
Right. Raymond?
Did you find that the prototypes have like a semantic, the prototypes themselves, like when you say like plot each patch in an image to the nearest cluster, do you find that the prototypes themselves are semantic?
So I thought I had some plots of that. I don't think so. It was a long time ago, but I think yes, but I'm not certain. Okay, let's not say something wrong. I don't know, to be honest. I don't remember. I think I plotted it. There might even be some plotting code in there, in the visualization code, but there's a PCA, joint PCA, dictionary learning, joint dict learning. Yeah, no, okay, there's none of that. Okay, so no, I did it, I think, but too long ago. I don't remember. The fact is that when you look at the features generally, either through PCA like that, or through other methods like this is a dictionary learning on top of the features to try and summarize the features, you do get very clean feature maps. So I think the clustering was good. The question is more like, do you get like 100 different clusters sharing the image and every small part of the image is in a different cluster? or do you get like 4 clusters separating the image? And I don't remember which one it was. So yeah, sorry.
Sure. Sorry, last thing. Did you ever try and enforce some property on the prototypes? Like
such as? Yep.
I mean, now with like SIGREG, you could enforce that they're all normally distributed in whatever space. You could do other things.
No, I didn't really enforce any property. I guess norm 1 is enforced, if I remember correctly. Yeah, basically the gist is that you want 2 things. You want them to spread around the space, the hypersphere, and you want them to not be empty or too full. You want the samples to be balanced on the prototypes.
Yeah.
And the sample balancing happens through the sync out knob that just is used in the clustering code to make sure that the clustering learns something that is balanced. And once you have kind of sample balancing, you also have the spreading around that happens naturally, because when you do a cross entropy like that, not only do you attract the prototype to one sample, you also push away the other prototypes to this sample. That is the denominator term. And therefore, basically, the closest prototype gets attracted and the other ones get pushed away. And so it just spreads away all the prototypes. You could still get something that is not really Gaussian if you have like some kind of dimensional collapse, just subspace collapse, where you lose a bit of rank. You could maybe use SIGREG stuff, definitely. Like, this was not out at the time. I don't know.
Sure. Thanks.
No worries. Connor?
Hey, thanks.
Hey.
This talk is really fun, by the way. Sorry to be bugging you with so many questions, but it's really insightful stuff. I like it. I mean, so I'm curious about these noisy feature maps. It seems to come up in a lot of methods, and it also came up in DINO v3, like where the features get noisier over time. I imagine you've thought a ton about this. Tell us your insights. What's the cause? What's going on?
Unclear. So first things first, I think, in a very, my opinion, like, and the team, not everyone on the DINO team shares this, but I think that possibly the DINO v3 problems, the DINO v2 problems are the same as the CAPI problems, just they don't appear as clearly, as crisply as in CAPI, because in CAPI you have such a simple thing that either it goes well or it goes wrong, and once it starts going wrong, everything crumbles. And you have very clear, I did not mention that, but the instability I was describing, I was calling that a regime change. Basically, you have a very smooth loss, like I was showing, and all of a sudden, it is not smooth at all, and it is just recognizable from the loss curve. So you can see at this point, you have a change of regime, and things go wrong. And so in DINO v2, v3, it's more of a smooth, like things start going wrong over time. But it might be the same phenomenon, just hidden away by the complexity and the other losses that stabilize. What might be the reason? My best shot at interpreting it was basically, okay. First thing is, it looks like we are losing locality of information. What do we mean by that? Is that the embedding of the patch of the head of the dog is slowly losing the meaning of head of dog, and maybe having a more general meaning of maybe the whole image or something like that. This is a dog with paws that look like that and has some kind of leaves behind him and these kind of things. You have some sort of delocalized information that starts happening. Why do I say that? Because, I mean, it's just the embeddings. When you plot PCA of embeddings, it starts lining up less and less with the actual image underneath. It's just, it does not look like it's the concept I'm seeing that is represented in embedding space. Now, why could this be the case? My best theory, and that Still don't know exactly whether it's true or not, but my best theory is there is some kind of problem of the encoder and the predictor not doing just their job. Maybe a question of capacity, but basically, let's say if the predictor is small and the encoder has a lot of capacity, once the encoder starts having a well represented the things like, okay, this is a head, I represent it well, it starts doing the job of the predictor instead of just doing its own job, and starts saying, this is not just the head of a dog, but this is something that is probably accompanied, like something that is probably near pose of a dog and the tail of a dog and these kind of things, and starts doing the prediction inside the encoder. Why does this not happen directly, like from the start of the training? Or this very separate design of encoder and predictor means that the encoder does not know where it will have to predict. Because the mass tokens are here, the positions of the mass tokens are stored here, and they are given to the predictor only, and the encoder does not know the positions of what it's missing. It knows only it's seeing a square, and it does not know if it will have to predict on the upper right or on the bottom left. And therefore, it has more uncertainty, and so it's harder for the encoder to do this prediction job. And so I think that's a very good thing. That's a good asymmetry to have that helps separate the encoder and predictor job. But maybe if you train too long, too hard, with not the right ratio of capacity between the two models, then you get an encoder that starts still doing this even though it's not his job, and you get this weird artifacts that start appearing. So what do you do against that? You try to make the predictor bigger. As I was saying, this was helping. You try to have higher masking ratio so that there's more uncertainty on the position of the mass tokens, and therefore there is more asymmetry between the encoder and the predictor. That was kind of working, was what I was doing. Also, I wanted to go towards making full inverse block masking, so you keep only a block and you don't see the rest. Why do I say that? Because, well, in this image, let's say if I hide the block in the middle, the encoder sees all the border of the image, and so it knows exactly what it will have to predict. Does not know where each mass token is going to be, but it knows the general region. Whereas if you do the opposite, if you keep a block and you have relative position encodings, you don't have any absolute position encoding, then the encoder just doesn't know where it is. And it might have to predict on the bottom left or upper right. You increase uncertainty, and so you might also discourage doing the prediction during the encoder. Was trying a lot to do that, except that in practice, if I don't use the roll, the circular shift applied to the mask, it just drops performance, which is against what I'm saying here, because if you use the roll, then you start having masks that are, for example, okay, if you use the roll on this one and you shift it one patch to the right, then you will have these two and these two, and you shift it one patch up, and then you have this one and this one and this one and this one, and now you have all the four corners, and you know exactly where you are in the image. And despite this, the roll was helping a lot, so it seems I'm missing stuff. Yeah, so that's my crackpot theory of what's going on, but it's not solved, as I was saying, else the model would be better.
No, that was great, and it helped me understand better why the inverse block masking and is useful. I mean, it seems like you would have the most uncertainty with the inverse block. You could go in any...
Yeah, it would make sense. I was really liking the inverse block masking for even other reasons. The fact that in the end, it's just equivalent to doing a cropping, and so you can like find very interesting links with the DINO loss itself, where you have cropping too. There's still an issue that is, as I was saying, there's a bias towards position. When you do inverse block masking, you see the middle and you predict the edges. And when you train on ImageNet type images, which is just what you always do, well, the middle is the informative part and the edges are not interesting. And so if you just keep predicting the edges all the time, you just predict grass half the time, and this is not really a super cool, good task for training.
Great, thank you. That was really fun to listen to.
Thanks. Paul, you had a question?
Yeah, thanks so much for the talk. I really like the thought process involved of like trying to simplify things. So you focus right with the IBOT loss, and obviously DINO has multiple losses. CAPI is not trained at all with the DINO loss or the colio. But what if you did? What if you made an ablation where you just swap out the IBOT loss?
So I had relatively early in the CAPI project, I had an experiment where I added it and it improved, and it was like nice. And then later, around the end of the project, I added it and it did not improve. And well, I did not have the time to actually like try to integrate things well. And to be honest, I was not that interested. Like I really wanted to try and fix this one and make it work really well to fix the instabilities, because I was feeling like putting a DINO loss on it was just putting duct tape to fix it. But a good cell loss should just work on its own, alone, and should just produce a good model. And so that was really what I was aiming for. But yeah, I think it should be very doable to make it work with the DINO loss.
Interesting. And quick follow-up on that. DINO v3, why are they still using IBOT loss? Why didn't they try using CAPI insights?
As I was saying, I tried putting it together. It did not help. So I guess it's very empirical driven, you know, like we try things. If it does not help, it doesn't help. I think people, like I didn't have much bandwidth for DINO v3. I was preparing my PhD defense and manuscript. And I think the other people didn't have that much bandwidth to dedicate to like trying out CAPI. So if it didn't work the first time, just didn't get adopted, and we did DINO v3 with iBots.
Okay, thank you.
Yeah. I had a couple of additional questions as well. So one question I had is like, yeah, you mentioned that the whole idea of the clustering is that DINO already kind of does this implicitly, so you want to make it more explicit. Did you do any experiments actually trying to add this explicit clustering to DINO itself, and what kind of results were you seeing with that?
I did not, but it's a very reasonable idea that I was thinking of doing. I did not really get the time for that. Yeah, I think it should work, but I don't think it's gonna bring much improvement. Why do I say that? Because I think DINO just works. Like it does not really need fixing. If it ain't broke, don't fix it. Yeah, I think the current formulation of the loss works for DINO. So I don't think having a cleaner mathematically formulation. I say that even though this thing is not clean mathematically. Like you could do something much more justified theoretically. I don't think having a cleaner formulation would help like bring you new signal that would make a better model. Plus, changing such a core component in DINO, you would need so much ablation work to be able to like find the right hyperparameter and recipe to be able to compare it with a current thing. I think by default it would be very hard to have to match DINO with a new component like that. So yeah, I didn't really try. But
Okay.
yeah, it could work.
Another question I had was that you mentioned that iBot, we talked about how iBot is unstable and does not work on its own, but at the same time, iBot was state of the art for a couple of years, right? So how did they get it to be so good and be state of the art, but in general it is quite unstable?
When I say iBot was state of the art, so the iBot model from the original iBot paper was trained using the DINO loss and the iBot loss.
Oh, I see.
No
So
one
it
ever
was basically
tried
like
iBot loss alone.
it was basically like a DINO v2 precursor.
Yeah, definitely.
Okay. And then one other thing I was going to ask was like, in the paper you talk about like CAPI obviously like doesn't really have any sort of global feature, and you have to do this sort of attentive probe to actually get some sort of global feature to do any sort of classification or stuff like that. Do you think there's ways to like add some sort of global feature directly into the model training, and have you explored that at all, or do you think like that's just not like the best approach of doing things? Like, what are your thoughts on that?
No, I think it should it's something useful, definitely. It's something that if you want to make the best ever model, SL model, you will want a global representation. Why did I not do it? Because I think it's solved. Not solved, but DINO does it well, like the DINO loss. If I want a global representation for my model, I will add slap a DINO loss on top of it, and it's probably gonna work. But until I find the right way to do my loss, I want to just consider only train my loss purely alone with no confounding factor, and that's why I did not really add the DINO loss on top of it. But my idea was always that this attentive probe, it finds how much ImageNet classification performance you could have if you had a good pooling of the patch features. Well, that's kind of what the DINO loss would be able to learn pretty easily, I think. So I was thinking, if you add a DINO loss on top of this model, you will probably get this kind of ImageNet accuracy with a linear probe instead of the attentive probe.
Okay, awesome. And then the last thing I was going to ask is that these for the predicting the masked patches, I want to clarify, are you predicting all of the masked patches, or you only predict a few of the masked patches at a time during training?
No, that's a few. That's kind of how it looks like here in this plot. That's what I was calling prediction subsampling. Basically, you just sample prediction positions without having to do them all. What is quite nice is that this is a cross-attention predictor, and so the tokens do not have any interdependency. So if you forward all of the mass tokens at once, or just one token one by one, they give the same result. And therefore, if you do prediction subsampling, like you only take a few tokens, it's exactly the same thing as if you had forwarded everything and then subsampled the loss term. And so it is a way to sample your loss term. It is just you are sampling tasks from a task prediction distribution, a prediction task distribution, and you don't need to have a million samples to have a reliable estimator of this. And so you do some kind of subsampling, and then you tune the subsampling ratio to your liking, to what is most efficient. I tuned it too hard, to be honest. In the paper and in the models, it's 5%. So I only predict 7 tokens, I think, out of all the missing tokens. Only 5% of the missing tokens are predicted. That's just too much. You shouldn't. I think something like 20%, maybe 10, 20%, predicting 20% of the missing tokens is a much better ratio. Just gives better performance without really any difference in efficiency. Because yes, this is an efficiency trick because you forward less tokens through the predictor. So I advise doing less prediction. That's what I was doing. Didn't have the time to correct it before the release.
Awesome. Thank you so much.
Pleasure. Varun?
Yeah, hi. Really nice work on CAPI, and I've used the repo myself. I would say that it is much cleaner than DINO V2 to use and pretty fast to get working on it. So my main question was regarding the batch size. So in the paper, you mentioned that you train with 16K batch size, and coincidentally, the number of prototypes is also 16K. So was 16K batch size chosen so that your clustering training is stable on teacher, or 16K was chosen just because you could afford more GPUs or higher batch size? So, and is there a correlation? Can I train a CAPI stably with 1K or 2K batch size? And do I have to decrease prototypes for that?
Yeah, it's a good question. So, the fact that the match is entirely coincidental. I don't have any passion for the number 16K. But it is correct that there is intra-batch dependency in the form of the sync-on-NUP algorithm. And clearly there is a link between the number of prototypes and the number of samples in your batch. Why do I say that? Because if you have 16K times 7 mass tokens that you have to assign to 16K prototypes, then the sync-on-NUP has to assign them exactly. You have enough to have 7 samples, 7 tokens per prototype. But if instead you have a batch size of 1K, then you have only 7K samples that have to be balanced across 16K clusters, and the balancing just does not work. You just can't balance that perfectly. So with self-balancing, it should be fine. But I think I don't know exactly what will happen, but I think wrong things might happen. Like the SK might not be happy about it. The SK in general is just more precise. It's just going to give a better answer when you give it a bigger batch, because it has a better estimation of the true distribution of the data over the clusters. I think you could devise some type of online SK that works across batches to be able to not need a 16K batch size. I entirely confess that this is a I did 16K just because I am GPU rich and I did not have to care about it. So I just wanted to train fast and use big batches. But yes, if you want smaller batches, my advice would be try with smaller batches. If wrong things seem to happen, maybe try some kind of online SK. Should be able to do.
So I was thinking, like, if SK is an issue to like a blocker to use smaller batch size, could we use centering and sharpening like the vanilla
like
Dino V1 way?
Dino, yeah, it's a form of. You can see centering and the centering. Sharpening is just temperature in a way.
Yeah.
You could see the centering as a form of single-step SK with an EMA estimated multiplier in the SK algorithm. It's a bit weird to see it like that, but it gives a bit of a. There's a bit of a link in a sense.
Yeah. Thank you.
You're welcome.
Awesome. One last thing I was just at like a very high level kind of thing is just like, what do you think the future of SSL is? Do you think it is still this sort of CAPI approach? Do you think it's continuing down modification of DINO? Do you think it's like more the JEPA approach? Like, what do you think like would be the future of modern SSL?
A good question, huh? Who knows? So what's certain is I think the future will be shaped not, I mean, as much by the science as by the people working on it. And the fact is that not many people have work on SSL right now, especially at scale. And so just the DINO team does good models and nobody beats them. So just whatever the DINO team does will be SOTA. And the fact is that the DINO team is absolutely not there's no God argument here. The DINO team is entirely fiable and they might not take the right path. And the field might take longer to correct than what the DINO team does. But as long as no one else is able to compete, they will lead the way. The DINO team has a very empirical approach in the sense that it does not give SOTA, it does not give SOTA, and like the goal is just to make a good model. So first, to make a good model, you have to try and start from the SOTA model, which is start from our SOTA DINO V3 recipe, and then try to improve it. And if you can simplify it while improving it, great. But if you simplify it and it degrades it, then it won't be adopted. And so the road to simplification is not easy while keeping SOTA interest. Now, the only serious competing paradigm in a sense is like the JPA team. I think they have GPUs with the new startup AMI. They focus more on video, which is a bit different, so it's not really a direct competition, but they are serious. They have good people, they do good work, and they have scale. But for now, it's they're struggling a bit to compete. As you've noticed, JPA and CAPI are just one and the same thing. It's just different recipes. So I like the JPA method. I think it is a very promising direction scientifically. If you ask me the question scientifically, I think JPA, CAPI style stuff is definitely something you want to explore. Can't say I'm certain it will be the paradigm, but I think it is my best bet. But yeah, we need to explore that with compute and attention to detail, and that's to make a very, very good model. It's just not going to be easy to find the right way to do things. The other question maybe included in that is, does SSL have a future? Because like people, there's just less people in vision than before because people move to LLMs. And the people that are still doing kind of vision are mostly doing like VLMs or multimodal stuff that is very separate from the SSL literature and not focused on the same questions. As I was saying in the beginning of the presentation, I think SSL has things to bring to the vision community that just are not solved outside of vision. But yeah, some people disagree. Quite a lot of people actually in the community saying that SSL does not really bring anything to the table that you can't get with another paradigm. Yeah, I do bet on, I keep betting on SSL, and in SSL I keep betting on CAPI style, JPA style stuff, but can't have certainty on that because well, it's just not winning yet.
Awesome. I think that's a great way to end. I think this was a really good discussion of SSL in general, and really appreciate the time that you've given us discussing this. I know we went like significantly over time too with all the questions, so I appreciate you staying on board to help answer these questions. But yeah, I hope everyone enjoyed the talk, and thank you again, Tim, for joining us.
Thanks everyone.
Bye.
Bye.